Ah, ok. No, pensavo avesse dimenticato. Ok? Good morning again, and I'm very happy to start the first keynote session, and very honored that we will have a very interesting presentation, and I will introduce shortly Professor Biswajeet Pradhan. He's brutal Indian, he was born in India, and after a period of 5 years in Brazil, in Germany, he is now professor at Faculty of Engineering of University of Technology of Sydney in Australia. Despite he's so young, he made a lot of projects. He also was supervised a lot of PhD theses, and also very impressive the indicators. For instance, Scopus, he has 118 H index of Scopus, also more than 800 papers indexed, very impressive, because normally these indicators are strictly related to the age, so young without white hair completely. Okay. And it's very interesting because the topic of this presentation is related to the artificial intelligence, geospatial artificial intelligence related to, in this case, with the application of natural hazard, but in disaster management, etc., etc. I call Professor Biswajeet Pradhan for having his speech.
Okay. All right. Very good morning. Still morning. Yeah, we just gone past 2 minutes after 12. Thank you very much to Professor Benjamino, Professor Soldo for inviting me. We just happened to meet 2 months ago in Kuala Lumpur while delivering a keynote talk. So he had his first keynote, I was the second keynote, and that's how actually he invited me. Okay, could you please consider actually to come to Hanoi to give this keynote talk? So obviously, because I'm so familiar with this part of the event, all right, so I'll come. So here I go. So thank you very much once again. Coming back to actually my look, I have no contribution to it. I must thank to my parents, right? So the young look or whatever. But nevertheless, it's not, sometimes the physical appearance can really, deceive. All right, so coming back to the talk, so what I thought that actually natural hazard is something very common. So I'll start actually, the first part of my presentation will be talking about some mind-boggling data about natural hazards, how it has been happening, how it has been affecting the community worldwide. So, and then how we could possibly use the technology, advanced technology, like machine learning with the help of geospatial data by and large to predict that. But not with 100% prediction accuracy, obviously, because otherwise we'll be knowing exactly where things are going to happen. But at least if we know roughly that where the next event is going to occur, we can be better prepared. So that is what actually the main objective of this kind of research. So this would be my talk outline. So first I'll be giving a little bit of terminologies, especially the data that, what sorts of data that we are using to come up with this spatial modeling and in order actually for us to produce the susceptibility, hazard, risk, and vulnerability assessment. And then I'll be sharing some applications from my own research that I have done in the last 20, 25 years. So focusing mostly on the geohazards, I would say that mostly meteorological hazards. So landslides, rockfall, gully erosions, and forest fire. So most of them, more or less, actually, we have used a combination of machine learning models, statistical models, and all other sorts of soft computing techniques for predicting these kind of natural hazards. And then I'll be just concluding my talk. So, as I mentioned, natural hazards, it's mind-boggling. Just to quote actually some data here, natural and human-induced disasters, they have been seriously increasing over a period of time. Although some people claim that climate change is a hoax, it's not happening. But obviously, if you look at these numbers, this is something that actually to ponder often. In 2016 itself, the total damage that was caused by natural catastrophes stood by $175 billion. It's huge. This goes past the GDP of many small countries. So that is the kind of number that we are talking about. So if you look at the data that is being shared by the economic damages from disaster as a share of GDP, which is released by the World Bank, you could see, so these are the different types of natural hazard that has happened in the last 100 years, over the century. And you could see that they have been steadily rising, not only with the frequency or number of times actually these events are occurring, but also the intensity is also getting larger and larger in terms of affecting the communities. So if you could look at all those types of geohazards, so the one that actually is clearly distinctive is the storms, obviously, because you have cyclones and those kind of things. And then the next one would be floods and droughts. Like in Australia, we have serious droughts. Sometimes it just goes for 20 years, 30 years. And these days also there are something called flash droughts. That means it's very hard to predict that because it just comes, just stay there for a couple of weeks and then it goes up. And during that couple of weeks, a lot of damage would have already done to the farms. So it is very important actually to monitor and to know that how quickly actually we could predict or we could know in advance so that we can be better prepared for that. So if you look at in terms of damage, you see on an average about $1 billion, you can put it safely, that is caused by the disaster. So this is the data that is from 1982 to 2023, and every 10 years that is actually the amount of damage that has been projected here. Look, it has been continuously, steadily increasing. Like in the last 3 years, 2022, am I all right? I didn't know. So it's too boring actually. So 2022, 2023, I see that is about $18 billion, right? And it has been increasing and increasing and increasing. So those who claim that climate change is not happening, I think it will be a strong debate on that, right? So if you look at, to answer to that particular questions, so this graph shows the trends of natural hazards versus the climate change, and you could see that the data that is coming from 1900 or 2000, so 100 years, you can see it is constantly increasing usually in terms of the number of climate-induced hazards. But obviously, earthquake they have increased, but it's not to that much. You can see that. But this could be also possible because we have information right now. We are in the era of information, so that we have a lot of data. Also, people are reporting, agencies are reporting that these events are happening, all right? But then, still, actually, the amount of damage has been severe, right? So, and among these meteorological hazards, the two distinct types of geohazards are very complex for that cyclones. And I think this part of the world, obviously, every year during the monsoon time, there are two monsoons that happens in the Southeast Asia, northeast and southwest monsoons, and during that time you have severe floods, especially every year there is a monsoon flood and actually damaging to the community. So interestingly, even the United Nations, they call it UNUSA in a short form. There's a long name to it. So they also have also a chapter, and that they produce the different kinds of hazard and risk map in a global scale. So, and that is a beautiful thing to do, because that means we can map it, we can know where exactly how the frequency of these events are occurring around the globe, and also both spatially and also temporally. So this is one sort of maps that has been produced. You could see that they have been coded into the colors, and for two passes, for earthquakes. So obviously, we are here, so we don't have actually much information about earthquakes. So at least we know that. But then tropical storms, you can see that there's all pretty crowded this area about the tropical storms. And then you have, but then this is a very large scale map. So obviously, if you want to zoom down, if you want to do the analysis in a very specific scale, or if you want to do, let's say, in a localized scale, obviously, the type of data and the type of analysis, the amount of modeling and techniques and tools that would be different. Okay, but nevertheless, these kind of maps would be very, very useful actually to give us some hands-on experience to see that, okay, at least where do we fall, right? So, and these maps are also useful for the insurance companies and so on. And especially in Australia, this is a mandatory nowadays actually to have, before going into development of a new area, it is good to have actually the geohazard map of that area. So, spatial models are getting very popular. So that's why I found over spatial intelligence. I think you guys are familiar with this. So, and then spatial intelligence has become a key because we are not just predicting something, but we are also with such a degree of accuracy. That's very important. And with accuracy, with some logical explanation behind it. That means we should be able to safely say why this particular type of hazard is occurring in these particular locations. All right, so those are the things that are very important. And obviously, for different types of geohazards, the type of input data we need to different. It's not just everything you could do under the carpet, right? So that, for example, the earthquake type of geohazard would be requiring different sorts of input data compared to the, let's say, volcanoes, or we are talking about landslides, or floods, and so on. Then the analysis method is also going to be different. So when I will be presenting the second part of my talk, you will be seeing, although we have so much mesmerized by this deep learning and new techniques, but not necessarily they will be giving a very good quality prediction when it comes to this kind of domain. So therefore, it is very important to understand how actually the model works and how they come up with this kind of analysis. Thank you so much. So the next one will be scale study. I have shown you it is a global scale. But again, if you are talking about a very localized scale, perhaps maybe one particular model may not be enough. So you maybe have to come up with actually ensemble models, complex models, where you have to, like integrate with the heuristic model, with a physical-based model, with the machine learning model, so that they can complement with each other. So those are the things that are very important. This particular slide shows a typical workflow of landslide hazard. So from here, more or less we can understand that how this whole process or how the modeling techniques are actually followed. So obviously the most important thing, what is required in geohazard modeling is the inventory data. Inventory data means the historical records of the information that has happened in X number of years. Historically, that is. Okay, so you can take this because we like to see it. No. All right. So we have actually the inventory is very extremely important because without that it's very hard to know actually how the interplay, conditioning that happens between the previous records and the different types of conditioning factors or input variables. So for example, in this case, you can see that there are triggering factors. In the case of landslide, possibly we have two types of triggering factors. One is because of the extreme rainfall or precipitations, other could be also due to the earthquake. The earthquake also could induce landslides as well. And then those are actually the triggering factors. And then you have environmental factors. So those are the conditioning factors, such as geology, soil, we are talking about morphology, geomorphology, we are talking about the lineaments, faults, and so all those number of variables are very extremely important actually to model them in our analysis. And then you have all separately the elements at risk, which would be requiring them to do the vulnerability and the risk assessment as well. So elements at risk means whatever it has got dollar or life attached to it. For example, like building roads, or infrastructure, so you are talking about essential facilities, the cadastral data or census data and so on. So these informations we need to collect them. They're very daunting. They're not very easy. And many countries, like in Africa, sometimes when we have PhD students coming from those countries, they do not have this kind of data, right? So, but using the indirect approach also, one could be able to collect those kind of information. So finally, we bring all this data, try to analyze them, try to establish the relationship between the historical events and all the input variables, conditioning factors, using different types of machine learning and artificial intelligence techniques, so that we can formulate a mathematical formula based in which we can predict an event for the future. So the input data, as I mentioned, they can be direct way. That means you go to the field, collect the data using the handheld equipments, but they are very expensive. And as you have seen that these events are occurring very regularly, so it's very daunting and also very expensive actually to do those kind of analysis. So therefore, these days we are using the remote sensing based tools and techniques actually to collect those information. So like for example, the drones, the micro satellites, and then we have the new generation satellites such as the Himawari, which collects the data in every 10 minutes global scale. So those data are extremely useful to monitor in a global scale as well. And then obviously now we have also the sophisticated modeling tools, AI tools, ensemble modeling techniques and complex model systems that could analyze this data, because you are talking about big data. You are talking about data. For example, when you are using the LiDAR data, laser scanning data, there are billions of points that need to be processed in a real time. So obviously, and because we have these facilities right now, it is possible. Perhaps 10 years ago, it was not possible to do that. And obviously, the software abilities also has been increasing day by day, and we are moving more from commercial software to the open source software as well. Now, as I mentioned, so these are some of the remote sensing based data capturing systems that is being used, such as drones, LiDAR. LiDAR is extremely popular, but again, it is expensive. But again, day by day, this is getting cheaper. As the number of users are increasing, obviously, the systems are getting cheaper as well. And then you have the terrestrial laser scanner, and then you have the mobile laser scanner. So those are very useful tool, handy tool, especially in a very quick way, very quick fashion way actually to collect the data about the environment. For example, if you put a mobile laser scanner here, within 15 minutes, you have like millions of point clouds. And we can generate actually 3D dimension of our room, this entire hall. So we are talking about large amount of data. So in order for us actually to analyze this data, obviously human beings by ourselves is very difficult to analyze and to understand them. So therefore we have to use the help of computer and smart computers. Then obviously satellites. We are talking about different types of satellite data. We're talking about hyperspectral sensors. Then we have these radar sensors, because especially in tropical countries whereby the optical sensors are not very useful, so the radar data is very useful because it has given the 365 days of data capturing ability. So these are some snippets from about this data I mentioned. So we all have seen actually the UAV data. So that's very high resolution, like 30 centimeter, 15 centimeters pixel size. Then you have the LiDAR data. This is being captured actually using the mobile laser scanner. You can see that a lot of data points that has been captured, and then obviously Google Maps and all of the sorts of actually data are very, very useful for this kind of analysis. Then obviously we need a platform, we need a software, we need a system in order actually to process this data. And a GIS is a perfect platform actually to crunch the data. Obviously, I mean, if you look back when I started my career 25 years ago, at that time GIS didn't have that ability actually to process this huge amount of information. Till today, GIS doesn't have that, the direct plugin of using the machine learning models straight away. We still have to do using the open source softwares like Python and other kind of software. So, but hopefully in years to come, so these are the things also can be improved. Then intelligence is becoming the key. We are not just talking about data crunching. We are not just talking about garbage in, garbage out. We are talking about predicting an event with accuracy, and should be also able to understand why did it predict. So that is why we can be able to come with a better accuracy, and we can generate new knowledge out of that as well. There has to be a degree of reasoning that why a decision has been made. And also, obviously, all these things help actually to provide a plan. All right. And obviously, it helps us actually to do the faster decision making applications as well. So the common AI models that are being used in natural hazards is, I think more or less whatever the computer scientists have invented lately, they're all being explored and being used in this domain as well. But obviously, I think large language models, LLM, and also the graph networks, I think those are the things still actually uncharted domain. But obviously, young researchers can be able to dive into this kind of areas actually to find out what are the capability of using these tools and techniques actually in this particular domain. So this is a typical workflow of natural hazard assessment, as I mentioned earlier. So you need the conditioning factors. Conditioning factors means those are the input variables that facilitate actually for a particular type of geohazard to occur. And then you have the historical records of that particular type of hazard. As I mentioned, so historical records means it is the inventory. And this is not easy to collect because let's say if I would be interested to know 30, 40 years of landslide records that has happened in the past, not necessarily actually the agencies who are like dealing with this kind of hazards, they will be having a detailed record. So obviously then you have to go back and look at the archive image, and then you have to also have the participatory GIS models as well. With the going back to the community, trying to understand, getting the perspective and the input in order to produce your inventory map. Remember, these machine learning models will just give you a prediction, but again, its accuracy and prediction depends on the quality of the data. Otherwise, it's just garbage in and garbage out. Okay, so therefore, the quality of the data, the input data, is extremely, extremely important. Okay, so once we have all the what you call the historical records, that is the inventory, and the conditioning factors, then we try to understand the relationship between them, like under what circumstances, under what conditions actually this particular type of event has occurred, right? So, and that we use different types of quantitative prediction models. It could be statistical, sometimes the simple statistical models also can be able to give you wonderful results. Or sometimes you need also to develop actually very complex models, or maybe ensemble models, because if the objective is complex, obviously. And then obviously all this can be done in a raster analysis, or it can be done actually in GIS to produce wonderful predictive maps. So with that background, so I guess we know more or less what we are talking about. We know what kind of data that we are talking about. We know that what are the conditioning factors, what are the inventory, and all that. So let me just quickly go through you, take you through actually some of the applications from my own research that has been done in the last 20 years. So I'll start off with landslides. So the first example actually is a contribution towards developing the inventory map itself. Because imagine if there is an area, now you do not have any inventory, now you would like to produce a landslide hazard map or landslide risk map. So obviously you need to have an inventory map. So when you do not have those information, can you be able to generate one using this remote sensing based techniques? So this is a case study in Malaysia, tropical place obviously. So it's a dense forest, thick forest. So obviously, if a landslide happens, very quickly the revegetation happens. 2 or 3 years later, you won't be able to see if there was any landslide that had happened in the past. So therefore, what we did was we used the airborne LiDAR, laser scanning. So we flew through the terrain, collected actually very high, dense laser scanning data points, and we know that the LiDAR is a very good tool that can penetrate through the vegetations, that can give you the information about the bare earth. So therefore, we use that, and then we derive actually some of the variables. So let me just quickly show you what is the techniques that we use here. We use an optimized neural network architecture, and we wanted to develop an automated landslide detection method. Okay, so what we did was, on the left hand side, you can see the data, the input data was LiDAR point clouds. And then when you are capturing the LiDAR data, obviously you also capture the very high resolution orthophotos. That means very high resolution photographs that can about 15 centimeter pixel resolution, which is fantastic. Okay, and then also you capture at the same time the texture information as well. So what we did, we just did not want to use one information, but we also wanted to use all combo informations, providing actually a composite patch. So we derived the LiDAR DM, and then we use the texture features, LiDAR point clouds and the orthophotos. Can I point? Pointer is not working. Okay, so now it is. Oh, already I have gone back. Okay. So, and then in this case, what we did, So we use FRG-based segmentation optimizer in the first step, and obviously there are a lot of steps that is being used actually to the ultimate aim here actually is to do the feature selection based CFS, correlation feature based selection. And after that, we applied to two different types of machine learning models. One is the recurrent neural network, another one is the neural network, which is, so we developed actually the model in one area, and then we try to actually use the transferability, try to test the transferability of the model in another area. See that how best that we could be able to produce actually, or could generate actually the predictive maps. So these are the architectures of those. I'm not going into very detail because it will be too much to digest. And so these are actually some of the results that you could see. The left-hand side, what you see is the result from the ANN model, and that is in the training area. Training area is where the best model was built, and this is the result of the RNN model. And you could see this automatically the red polyzones that has been detected as the potential landslide location areas. Okay, and then when we transfer the model into the test area, obviously doesn't, as I mentioned, doesn't give you 100% accuracy. Whoever claims that it can give you 100% accuracy, I would contest. It's because terrains are different, they're complex. Okay, so 100% accuracy in a natural environment is impossible. Okay, so we got about excess of 80% accuracy, which is good enough to produce a preliminary landslide inventory map. At least you have something now. Now, by taking it as a foundation, then you could obviously add on values to it by improving, going into the participatory, going to the community, interacting with them, or maybe look at actually all these newspaper cuttings and see that if there is any incident that has happened in the past, you could actually add on those information attached to this inventory. And then not only the model that we developed actually produce these, but also it gives you the most relevant features that actually is contributing towards the for this analysis. So as you can see, standard deviation of the DTM rank 1, and then the mean slope rank 3, and so on. This is another case study. The study area is here in Vietnam. So I had a PhD students many years ago. So we did this thesis in landslide hazard and risk assessment. So this was the paper that was published in Geomorphology back in 2012. So it's a long time ago. So in this case, what we did was, so we used two different types of model, and that time actually the Leavenworth market model was getting very popular. And so we wanted to compare with the Bayesian regularized neural network. And if you look at actually visually, both these outputs, they look almost similar. Okay. But if you look at actually in terms of prediction accuracy, you could see that the Bayesian regular neural network gives about excess of 90% prediction accuracy. And I mean, they are almost similar, but again, can we improve further? So obviously, we can use maybe the new generation models, machine learning models, probably we can improve the accuracy into better accuracy. This is another paper that I'm going to just quickly present to you. This is in this paper, what we did, we used the CNN, convolutional neural networks, using Bayesian optimization for landslide assessment method. So in this case, we used the 1D CNN, and this the study area actually was in South Korea. And random forest model was used to identify the significant landslide conditioning parameters. That means which parameters contribute most actually to the modeling purpose. And then obviously we did the optimization using the Bayesian, and then the validation was done. So these are the results. As you can see in the table that shows the different types of input data that was used, you can see that landslide locations or the inventory data. Then we have the altitude, slope, and they're all in the 1 to 5,000 scale. So obviously it's a very good quality data that was used. Then obviously there are more than 20 parameters that was used. And finally we produced this landslide susceptibility map. And in terms of accuracy, the one actually using the CNN, convolutional neural network, produced the best accuracy is close to 88%. Right? This is another case study of, in this case, we use the landslide typology, because when you're talking about landslide, it's not just one type of landslide. You have different types of landslide. You have rock faults, you have debris flow, you have rotational landslides, you have, all other types of landslides. So in this case, we wanted to enhance the susceptibility map using the landslide typology, using ensemble machine learning, stacking ensemble model. So in this case, our contribution was to by producing the stacking ensemble machine learning model. So we can see this looks a bit complicated, but it's pretty straightforward if you want to see. So there are about 733 landslides were classified, and the study area was in China. What is that area? I'm forgetting actually. And different types of machine learning models that you use, and out of that, obviously, then you combine them using the structural model to produce a better quality landslide susceptibility model. So the data source was used derived from different agencies, different source data like topographic map, geology, field investigations, remote sensing-based information, historical landslide inventory map. There are about 16 conditioning factors or positive factors that were used, like altitude, slope aspect, and blah, blah, blah. Then what we did was, then all these landslides, they were actually, like they're separated into 3 different types of landslide, like landslide type 1, 2, and 3, which is reservoir affected, non-reservoir affected, and rock falls. And then we did the feature selections. Because when you're using X number of data, so basically sometimes there will be double, triple counting of the data. So therefore, the feature selection is very important, making sure that you are not counting the same input data twice, triple times, and they have been useless, right? So therefore, the feature selection process was important. And then we split the data into training and sample data about 70-30 because we didn't have too many number of records. Obviously, if you would have in excess of thousands, probably would have gone into 50-50 training and testing distribution, sample distribution. Then you use different types of machine learning models to produce the result. In terms of accuracy, in this case, the deep learning model outperformed all the other type of traditional based models. But again, for the training, it gave in the excess of 90%, about 92%. This is fantastic. So this is the one here. There is another paper. This is very latest work because XAI is very getting popular in the last 4 to 5 years. So interpretable XAI, because artificial intelligence, because urban planners, they always ask questions that why this particular type of variables is giving you, high weightage or so on. So you should be having that answer. Your model should be having that answer, explaining that why this particular type of reasoning has been made. So in this case, we developed this model for landslide susceptibility modeling was published in Applied Soft Computing last year. And so it was tested in a region of South Korea, which is about 89% accuracy. And interestingly, you can see here, landslide had a very negative correlation with the altitude, because altitude is something also always, more than 95% time, it would always give a positive correlation. But in this case, it had a negative correlation. So therefore, it is not actually, you cannot take the decisions actually as a very generalized way, because it's a very case-to-case basis. So this is the entire process flow that how actually we build this model. Obviously, we had the landslide inventory map, and then we have landslide influencing factor, conditioning factors. There are about 25 landslide conditioning factors that were taken into consideration for modeling, and you use the Sharpley to understand actually the contribution of each conditioning factor into the outcome. And the accuracy that was given was what, 89%. Then this is another case study. This is from Bhutan. So this is different type of terrain, different type of geo environment. So again, we wanted to use the same XAI kind of method, but in this case, we wanted to use the time series SAR dataset. So as I mentioned, the dataset is different because depending on the terrain, depending on the geo environment, sometimes the idealistic type of data may not be available. So therefore, you have to have whatever data that is available, that you have to make use of them in order for us to produce. So in this case, explainable AI was used, and that was used using the time series data, remote sensing data, and Sharpley was used as an what do you call XAI technique. And 36 features were derived from different sorts of remote sensing data, like ALOS Pulsar, ALOS 2 SAR data, Landsat 8, topo maps, and digital elevation model. And then we try to understand actually how these parameters are behaving. So this is the results, and you can see more or less is about 91% actually, and 94% accuracy that is giving the random forest, and support vector machine is giving around 91% accuracy. So this is the study area in Bhutan. So that's very quickly about landslide. Let me just quickly show you some examples from other type of landslide, which is called the debris flow. And again, this is a case study that was published some time ago, some years ago, and we developed actually the data mining based approach for debris flow susceptibility model. So in this case, we use the airborne LiDAR data because again, the electropical setup, so very hard actually to use the 50,000 or 20,000 contour data because they're more or less useless for this kind of assessment. So we use actually very high resolution airborne LiDAR data. And from there, we did the filtering and everything, and then we come up with the digital surface model, digital terrain model. And then we have some inventory data that we use actually for the training purpose. In this case, we use two types of machine learning models. One is the supercomputer machine, another one is the mass model. And then the debris flow in the first stage, what we did was we tried to optimize to automate the process of identifying the potential debris flow areas using the LiDAR data. Okay, because and then after performing that task, then we come up with the debris flow conditioning factors like the elevation, slope, aspect, curvature, and all those. Then we did the multi-collinearity test. After doing the multi-collinearity test, then we did the we come up with the debris flow susceptibility model. So as you can see here, this is then finally we did the runout distance model. So the first actually is the potential debris flow source area on the left hand side, because I was asked not to move, so I can't. So on the left hand side, and then you have the other kind of information that is maximum flow height, maximum velocity, pressure, and momentum. They are being calculated using just the LiDAR based information. And this is fantastic because in a case of debris flow, you would like to know that how far actually the flow is going to, how much of volume of material is going to be detached from the source area. So all those things have been calculated in a catchment scale, but this can be also done in a very small catchment as well. And this is how actually the information can be presented actually on the digital television model. And you can see that that is the road on the left hand side, and if that is the source area, then you can see how much of material that is going to come. And also you can simulate that how long will it take actually to go and hit the settlement, or maybe the potential road or whatever. So then we did the simulation. So you did the numerical modeling, as you can see here. So if that was let me just come through again. Sorry. So you can see that if this is the road, that actually how much of material. So obviously those kind of informations are very useful to do the mitigation strategy. So at least we can put the nets to stop actually from the material being detached, and they can be collected without coming and being hitting actually the highways. Then it can be, as I mentioned, it can be also done in a very small catchment studies as well. This is what we have done in the same area, and we then develop actually the model for a town, and you can see that some of the debris flow it goes actually about 1 kilometer far from the township. Sometimes we see that we might think that there is no potential threat, but there are some threats that is coming even up in the hill and it's running actually about 1 kilometer distance. So those sorts of information and mathematical modeling can be very, very useful to produce this kind of information. So the next application is rockfall study. I don't have to explain what is rockfall. So we all know, again, the study area is part of Malaysia. Why I'm showing actually a lot of examples of Malaysia, because I was sitting as one of the, I had multiple projects there. So out of which that we collected a lot of data and a lot of test bed, actually we did while developing this model. So this is a case study you can see here. So in this case, this work was published in Landslides in 2018, long time ago. And the LiDAR data again was used. So in this case, the scanner, the Regal LMQ 5600 was used. And the point density is about 3 to 4 point density. But I think these days now, probably we have much more larger number of point density. And height of flight was about 1,000 meter, about a kilometer. And the camera type was Hasselblad, and camera angle was 45 degrees. So while collecting actually the point clouds, we also collected very high resolution photographs, which the spatial resolution about 13 centimeter. So it was very useful actually to perform the analysis, especially to produce a very high quality land use land cover map. And then those are also very useful for the identification of potential rockfall source areas, or what you call the cedar points here. So these are some of the results. You can see it's the digital illumination model, then slope, and then the terrain type, curvature, and I'm not going into very detail about the process what we have done. So in the first phase, what we did, we potentially identified actually the rockfall potential areas, and then using them, we developed the rockfall hazard assessment. So this work was published in Catena back in 2019. So what we did, we calculated the rockfall frequency, then the rockfall energy, that what is the energy of this rockfall, how far it can be able to bounce and go far, and then finally we come up with the rockfall hazard. So again, these sorts of information are very useful actually for mitigation strategy as well. Then the next one would be gully erosion studies. Again, this is a different types of hazard we are talking about. So in this case, we use the RNN and the GRE deep learning models to map the land susceptibility to gully erosions. So again, in this case, we use the three novel measures based game theory like SHARP, CPPD, profile, and PFI was used to interpret the deep learning models. And but obviously the results showed that the RNN model performed better than other type of traditional kind of models. This is, you can see that the different types of input data that was used, like slope, SPI, stream power index, TPI, topography power index, then TWI, wetness index, then LS factor, dissolution, clay information, sand, silt, gulf density, all those information that we use. And then we use the feature selection with the Boruta algorithm, because this is also very powerful. And then we come up with which features are contributing to the more. In this case, dam, landslide, slate, and these are the parameters actually they contribute to the more. And finally, we apply the model, the machine learning model too. And then after performing the model, we use the Sharply to interpret the results from that model. And then finally, we produce the gully erosion hazard map. So as I mentioned, the RNN model performed the best results in excess of a 90% accuracy. And so these are the different plots actually that justifies the how actually the result has come. This is another case study using machine learning for gully erosion susceptibility mapping as well. The study area is in somewhere in Morocco, as you can see. And then again, different sorts of machine learning models that we use, random forest, supported to machine. Now the question comes, why we use different types of models? Because again, it's not that, as you have seen so far, because it's not that this is that particular type of machine learning model, like what the computer scientists use that can, especially in this domain, can always give you a better result. No, not always. So therefore, it is very important actually to know that which are robust models and consistently can be able to give you the best results. So again, similar kind of process that we do, different types of parameters that was used. And finally, the gully erosion susceptibility maps were produced, as you can see here. So again, in this case, random forest gave the best result, about 90%, 89% accuracy. So what you see is that different types of maps, they are all being used using the different types of machine learning models. Now, after going through landslide and this all that, let us actually look at different types of hazard. That is the forest fire. Australia is very famous for, and also Canada. And in the US, forest fire is a very common type of disaster. So this is a work that was published last year. So use the XAI for interpreting the contributing factors that fed into the wildfire susceptibility prediction model. In 2019, we had one of the dark summer, whereby actually, we had one of the biggest fire even in Australia, like killing about couple of millions actually kangaroos, and also the native, other kinds of animals as well. So that costed about $200 billion actually to Australian economy. And so therefore, we just wanted to do those analysis. We wanted to do the wildfire susceptibility prediction using the deep learning, and the study was Victoria, Gippsland. So there are 11 prediction factors that we used. They are all categorized into 3 types. One is the metallurgical, topographical, and land cover or vegetation related materials type of factors. And in this case, we use the deep learning, and the Sharply was used actually to interpret the model outcome. And this is what you can see. Interestingly, humidity also plays a very critical role as well, and the drought, cold, and also the wind speed, rainfall. So they are all actually gives actually significant contribution towards this model building. So there are a lot of other work that we have done in the forest fires, but then for this keynote, I just picked up, actually selected a few case studies. Let me just quickly show you that also this can be used extensively in flood assessment as well. This is a paper that was published last year again using the Excel, because as I mentioned, Excel is something very new, right? So that's why we are trying to explore into different types of geohazards. And in this case, it was flood, and the study area was in Korea, South Korea, because we have a lot of good quality data sets there. And in this case, we develop a hybrid deep learning model, machine learning models, and the different types of flood conditioning parameters was used, and obviously flood inventory data was very crucial. So there are about 3 different types of conditioning factors, like geographical, vegetation, and soil type of material conditioning factors that were used. And finally, SHARP was used actually to understand the result outcome that was coming out of the CNN model, and then we did the validation of the model. So interestingly, it gave an accuracy about 88% accuracy. Then this is a case study in, again, this is a 2014, there is a major flood that happened actually in Malaysia. So we wanted to map automatically how the flood scenario had changed over a period of flood season. So we used the temporal radar imagery, and we developed actually the machine learning model to understand and identify just flooded areas. And as it looks so simple, it's not, because flood and the water bodies will be always confused. And when you are training the machine, it will be very difficult to understand for the machine that which one is flooded water and which one is just the normal water conditions. So this is the results of that. And then there are another case study that is from Iran, in Sari. We developed actually the risk map in this case. Earthquake studies, again, we have done a lot of work in this domain as well. This just quickly show you, and then I can skip the other, and I'll conclude my talk. So in this case, do you remember actually the 2004, the massive tsunami that happened in December 2004, where many Asian countries were affected? So, and out of that, we had a project actually to understand and to do a risk assessment, detailed risk assessment of the Banda Aceh. Aceh is the place that is actually, the epicenter of that earthquake. So there are a few papers that we have published. So this is the Aceh, the Sumatra. Then we wanted to come up with a very detailed risk map of that. So there are different types of assessment modeling models that we developed, like earthquake probability, then seismic susceptibility assessment, then earthquake hazard assessment, then earthquake vulnerability, and earthquake risk assessment. Different sorts of input data that was used to produce this kind of information. And then in the case of vulnerability, we developed 3 types of vulnerability: special vulnerability, structural, and geotechnical based vulnerability. A lot of geodata actually come into place, especially the type of building, the type of materials that they were used, and so on. And finally, let me just quickly show you the results. So these are the results from the social vulnerability, structural vulnerability, and geotechnical vulnerability, and we combine them to produce a earthquake vulnerability map. Then finally, using them, we come up with the earthquake risk map, and the accuracy was detected as about 84%. Then there is another earthquake that happened also lately in Palu. So, and that was actually, that is also what we wanted to understand as well. And in this case, the damage was not because of the earthquake itself or the tsunami itself. It was due to the, what you call that, I'm not getting that term actually right now. I'm not getting that term right now. So in this case, again, similar kind of models, the machine learning models that we used, and then we produced a different sorts of risks. That means we simulate the different type of risk. So these are the different factors that was used. Very quickly, I'll just show you, and then finally, we created actually the risk map, 2 different types of risk map. So the accuracy is about more than 85% accuracy. Then this is another case study. In this case, earthquake-induced liquefaction hazard. So the previous one was liquefaction. Okay. So this is we did it actually one of the first study that we did it in entire Australia, and then the result actually was like compared with the result that is being used in Geoscience Australia. And the liquefaction hazard map was estimated for 50 years with 2% and 10% incidence rate. So this is the data, and then this is what actually the results looks like. So our contribution is these 2 maps that these 2 types of predictive maps that we produced using the and the result shows that Western and Southern Australia is very prone to actually this kind of disaster. So similarly, similar type of actually analysis can be done, have been done in like coastal disaster modeling as well. Just quickly to show you, because this is also Vietnam area. This is a detailed analysis that we done at the eastern coast of Bangladesh for the coastal vulnerability risk assessment. Okay, so lots of data, how the coastline had changed in the last 50 years or 100 years, we have mapped them, and then we did a detailed assessment as well, and finally we produced the entire coastal area was marketed based on actually the vulnerability. Then cyclone risk assessment also has been done using this machine learning and geospatial techniques. This is a work that has been published in 2019, Science of the Total Environment. And the data that was used, the elevation, slope, and the proximity to coastline, and the cyclone coming from the past and so on. Then finally, we produced 4 different types of maps like vulnerability and exposure, then hazard, mitigation capacity, and risk. This is very important because this kind of information will help you to understand whether the community, specific community, is ready to cope if there is a particular type of hazard is going to happen. Coping capacity is very important. Because, like for example, when an earthquake happens in Japan, the coping capacity is very high. You don't have to worry about it, right? But if an earthquake, let's say 5 to 6 Richter scale happens, like in some part of the world, the coping capacity is not there because they don't follow the building designs and so on. So obviously, it becomes very difficult. So I have shown you very quickly. Sorry that I had to, because he's only Benjamin showed me 5 minutes, so I had to just quickly wrap it up. So although actually a lot of opportunity here in this domain to use machine learning and geospatial intelligence to produce, like risk assessment, vulnerability assessment, spatial temporal risk modeling, and so on. But still, actually, there are a lot of opportunities as well to more develop into actually and explore this domain as well. So data itself is a problem, as we have seen that not every part of the world we have a lot of good quality data. And then real-time data analysis is a big problem because we are talking about a lot of data coming in the real time, how quickly that is processed, and then not only processed, but also the output has to be verified and to be relayed actually to the relevant agency so that the necessary action can be taken. So that is still actually a lot of challenge. And again, as we have seen, the historical data records are still a big problem. So that could be a lot of contribution can be done in terms of contributing to developing inventory data in different types of geohazards as well, and multi-hazard assessment. Like for example, imagine, let's say an earthquake is happening. The source is earthquake, but the earthquake now leading to actually a dam failure. Now the dam failure is leading to flood. Then at the same time, you have some landslides coming in, maybe some glacial hazard coming in. So this just one triggering factor now actually is now creating actually a lot of different types of geohazards, right? So more and more geohazard assessment is what you call the multi-hazard risk assessment is also coming into foray as well. So moving forward, we can just wish that and hopefully that more and more data would be would be at our hand, would be readily available for us researchers so that we can do wonderful research in this domain. Then standardizing the data is another critical issue because the data coming from different sources, different agencies, they have developed the data for their own specific purpose in different scale. So therefore, standardizing and harmonizing the data is also very critical. And multi-hazard modeling that I have mentioned, open source model actually, that is also very important. But I think now the Python is very, very popular, so that's not an issue. And as I mentioned, real-time assessment is also is a way forward as well. Optimizing the model, understanding more about explainability of the model outcome. There are a lot of actually opportunities in this space actually to explore for the young researchers as well. So with that, thank you very much. Once again, I'm still standing between you and your lunch. So yeah, thank you very much.
Thank you so much.
Any questions? I'm very hungry now.
No.
Can you repeat your question again? I know you're talking about the data. So what is the question again? Can you generalize the data? Different countries. Yeah. Okay, thank you. Thank you. I'm afraid that, as you mentioned, that a lot of data are already available. No, I'm afraid it's not. Obviously, a lot of developed countries, we have access to a lot of data, but in the threshold countries, developing countries like Africa and like Caribbean countries, there is not much data that is available because it needs a lot of resources to collect this kind of data, right? And again, like collecting data, information using the high resolution LiDAR and all this, it needs a lot of effort, dollars. So that is why lately you can see that a lot of journals are focusing on building the data set system. There is a journal called Data in Brief. Have you heard about the journal called Data in Brief? So that journal focusing just about the data. That means contributing towards the data development. Okay. So if you are developing a new set of data, you can always submit those kind of journals and very quickly they actually assess and publish those. So now coming back to the second part of the question is that can we generalize? Yes, we could, but then what happens is that it would be a very different scale. Like the world map that I showed, right? That was a scale about 1 million, 1 million, right? So you get a rough idea, okay, where, but exactly, but then when you're talking about 1 million scale, how can it be useful in terms of, doing a proper mitigation strategy, right? A community gets affected if a small landslide happens or disaster happens or flood happens, right? So therefore, it's very important to do in a very detailed scale as well. So in those cases, I'm afraid we can't avoid without actually creating a good amount of data set, right? I've been fortunate because I have had projects in different countries and students coming from different countries. So we have developed a lot of data set, but still I would say that it's not enough. Even if you look at the landslide, like world database, it's not still a lot of things to contribute as well. And unfortunately, some of the countries like Southeast Asian countries, Western countries, the data is not being shared very easily. Within the agencies, they don't share it with each other. They feel that it's their own, it's their own property. So because they would have maybe spent the project, to collect the data, and they just keep to themselves. Like in Australia, I know that in Europe, whenever when we produce some data, it's a mandatory that the result has to be made public, right? Because it's being used by the taxpayers' money, but not in these certain countries. So therefore, it's still a lot of challenges.
They automatically have different type of features and everything. So they think it's good to use it as a mission scale for optimization.
100%. So you could see actually some of the results that I have shown way back maybe 10, 12 years ago when the machine learning models were, the new generation machine learning models were not developed, right? So lately obviously we could use, but again it's not we can't generalize because it's a very, very like terrain specific, right? Because the geo environment varies, right? In certain geo environment, maybe certain kind of conditioning factor actually contributes more to producing a type of geohazard. but if you go, let's say 100 kilometers far from that area, might be there is another solution that will be contributed, right? So it's not that like all the data scientists use the data. No. In this case, in this specific domain, it is very, it's very important actually to understand the data and the interplay and how the triggering mechanism is happening to produce a particular type of geospatial. Okay, but coming back to the question, yes, we could use absolutely. Yes, John.
Thank you for the very just wanted to let you know and the accuracy that expressed and so based on that, you are like one was
Thank you, John. I'm forgetting questions, so please remind if I need to. So the first question was, let me just answer the second question first, because I remember. The applicability of the models. So many of the models that we have developed actually with the Department of Works. So those are the agencies. For example, like the work that I have shown from Malaysia. This is a model that was developed for the Department of Works and also the Department of Geology and Mineralogy. So they are using actually. So we have. I've just shown you the scientific part. But when we are developing model for a commercial purpose, for them actually to use in a day-to-day basis, operational basis, so we have automatized the process. Because agency, they wouldn't have actually all these, like manpower to do all these processes. So they want as much as automating the process, so that minimum investment is coming from the personnel as well. So, for example, like we have developed using the very simple user interface, using the ArcGIS and developing these in the back end, developing the machine learning models and feeding the input data, and then just for the visualization purpose, you use the GIS. So yes, they are being used. Okay, coming back to your first question, yes, 100%. Because what I have shown you here today is mostly about spatial prediction, but temporal prediction as well. So there are a lot of work that we have done with spatial temporal prediction. So we are not talking about the where actually the landslide is going to happen spatially, but also when. For example, let's say cumulative rainfall goes beyond 100 mm, 100 mm, or 120 mm, or 130 mm. So these are the particular topics. These are the rasters or the areas that is actually to look out for, because these are the most potential areas that actually the next landslide is going to happen. So that is why actually we do the analysis in spatial temporal assessment. Okay, thank you.
Thank you for the presentation. I have a number of just one question. There is a map. And mainly natural arts probably public administration and the responsible bodies of security and so on. But in many other sectors, other clients, not we which those things just when just be it is the case where the users must have to go there with good body information. So if your set they give you trust. example how they perceive and plan.
Thank you, thank you. That's a very, very interesting question, actually. So I'll just give an example to answer your question. Like when we are developing, let's say, a risk assessment. Let's say landslide has happened and maybe a flood has happened, right? So now we produce this information actually in a maybe in a localized scale, or maybe in a like county scale, or maybe in a district scale. But when it comes to, let's say, a road has been blocked because of a particular, like debris flow, landslide, rock fall, right? So now there is a particular community, maybe 3 or 4 or 10 houses. They are not directly involved with landslide. Landslide has not gone actually destroyed the community. Okay. But now there is an indirect actually risk assessment there as well. Because if there are, let's say, about 5, 6 people who are the wage earners or the breadwinners actually coming from the family, right? So they cannot go to work for X number of days until actually the whole situation come into the normal situation, right? So those are the information need to be integrated as well. That is where the social part comes into play. Okay. So therefore, I made a statement during my presentation that yes, this is a spatial problem because everything, the whole approach can be done through spatial. But again, the data coming from different sources, right? So that is something that actually I would say that yes. Now coming back to the talk, it's still a debate because look, whatever academicians do, I don't think actually 100% people trust. They will come and saying that, oh, how you publish a paper, maybe Nature publish a paper in a very 15 impact factor journal. But then, so can it be really insurance company? Because they would try to see their kind of benefit, right? So they are in the other side of the domain. Okay. So even for example, there are some hardcore civil engineers, the geotechnical engineers. They don't like machine learning at all. They refuse to accept machine learning at all. They say no. They still like that traditional way of developing the geotechnical based assessment. But hey, can you do that actually in a large scale? How much of effort, how much of resources, how much of dollar, money, power needed actually to do those kind of analysis? So the answer to that, by developing ensemble models, you can't actually neglect them. The inputs are equally needed, obviously. But then what you can do in that case, you can integrate between the physical-based model, okay, which is their domain, and then bring in machine learning models, try to understand actually what these physical-based models are doing, and then derive actually some good insights, develop actually mathematical solutions so that you could develop, like using both aspects. Okay, so that would be my answer. Thank you.
Okay, very much. There is other things. First of all, first is map, forest maps. First maps to the national assets to begin. That's to mention the forest maps. But machine let you know. It's not forest fires. The first map. The second is that we must agree that for innovation, for every there is no possibility of failure. No. The second is the question of the fault. For the prediction has a specific prediction without when is supposed to select prediction or earthquake or a landslide without saying in 3 days, 5 o'clock, so that will be 4 more 8%. So if they say that you want 3 days, all you say was after using your methods, the then CCP anything you can do just you may have awareness. You may have awareness. That's all it is. Okay? So,
good question. I was expecting that. Good. So coming back to the prediction, right? Earthquake, 100%. I never said that actually we predicted an earthquake. No one has done that. You said that probability estimation. Mind you, there is a totally different kind of terminologies here. Okay. And what I presented here was an earthquake risk probability. That's totally different. Earthquake predictions that you are telling that okay, at maybe 2 days from now, at this particular time, this particular fault is going to rupture, and this is at this particular depth, and this is the intensity. No one has done that. If I would do that, then I think that would be first to be published in data, right? So it's not. I think it's a wrong comment. Second thing. So, but I was very clear. Second question, susceptibility, right? So a lot of work that I have shown you is the susceptibility, and also to certain degrees of it. So as I mentioned, susceptibility. So when you look at actually the risk assessment framework, right? So the first stage you do the susceptibility. That is also probability estimating likely. That is what you are referring to. That means everything is when you break down between 0 and 1. 1 is most likely, 0 is known. Then the next step actually, this is the spatial prediction that we are doing. Spatial prediction in the sense that most likely where it is going. So coming back to his question, also like what Joanna asked. Next is when actually trying to bring into the temporal scale, right? That means bringing the figure in factor. When an earthquake happens, let in the case of landslide. Well, in the case of, let's say, there is a rainfall event happens, okay? 100 mm of rainfall, cumulative, maybe 18 hours, okay? Antecedent rainfall. These are the areas exactly where the landslide occurred. This is where actually we do the other estimation. I have not presented actually from results here, but yes, 100% you can do that. It is 100% you can do it. That's not a problem. But I'm not saying 100% prediction accuracy, but you could predict to certain extent, with certain degree of accuracy. Okay, but look, even I would say 60 to 70% of prediction is already very good enough. Because if the community is being already informed, the degree of damage that is coming from that particular event will be totally different, right? Okay, so that is the thing. Now the third question, what did you ask? I'm forgetting. No, I think I already answered. Yeah, I mean that is so obviously. Okay, coming back. So the time stamp. So the time stamp. So the time stamp. Yeah. So look, this is where actually people coming from different backgrounds. A social scientist who understand the terminology is totally different than a civil engineer, and a spatial scientist is going to be totally different understand than a computer scientist, right? So it's debatable. Coming back actually to the map that you mentioned, right? So, so the first map actually where the United Nations and all these what do you call? Yeah. So they have not done actually for all obviously. So they have done the one that is more or less the global scale of that, right? So I don't think what they are like Bibles or they are like Qurans. No, they are not, right? So they have just given it value, and there are a lot of work that has been happening. And they also, I know, I was with them 15, 17 years ago, you know, this United Charter of UNOSA, and they at that time they are actually having specific community-related workshops in the threshold countries. I hate to say underdeveloped countries, or I would say threshold countries or developing countries. So the idea was as good as you predict something, I will share that. But if the community is not ready for it, if the community is not doesn't have the coping capability, it's useless. You know. So as I mentioned, this is a very complex thing. This is biohazard. When you're dealing with biohazard, it's a very complex thing. And no one is saying that you can predict something that with 100% accuracy. No. Even a computer scientist also cannot predict. For example, I have a student who are working in the banking sector. Okay, oil mortgage. I have some couple of students working because I'm curious. Now that I have worked so much in this domain, I would like to understand actually how these things happen in the different domain. See how the mortgage price also varies. You can't predict it. It's a demand. Look, now if you look at the historical record of 100 years, right? But now here it comes 18 years time. And I need this because my wife wants it. My child wants this house because he likes it. That's it, I throw money. So all your predictions go wrong, right? So meaning to say that it's but somehow with certain degree of accuracy, we can. Very interesting question. Thank you.
We have yes, all week about 2 weeks.
But
one of the discussion, let's not do the ones, but we can also discuss the story and
okay, now